Unit 1, matrices. 1.1 is adding and subtracting matrices. We start with the size of each matrix. Write this down. Rows before co's. A matrix is a bunch of numbers organized in rows and columns, and it's going to be helpful for you to remember rows come first. Think about rows before you think about columns, rows before co's. So when example 1 says give the size of each matrix, what you want to do is count the number of rows. So I see 1, 2, 3, 1, 2, 3 rows, and 1, 2 columns. So 3 rows, 2 columns, rows before co's, we're going to call this 3 by 2. Now that does not say 3 times 2. It says 3 by 2. 3 by 2. Tell if each matrix is square, a vector, or neither. We'll come back to that. Let's look at part B. Matrix B, you've got 1, 2, 3 rows, 1, 2, 3 columns, so the size is 3 by 3. I think it's kind of obvious that this one's a square. This is a square matrix, and think about why. A square has the same width and height, all right, length and width. And so since those two numbers are the same, 3 and 3, that's a square matrix. Part C is going to be a vector, but keep going the same. Look, there's only one row, but there's 1, 2, 3, 4, 5 columns. The size of this is a 1 by 5, and this is a vector. But specifically, since it's just a row, we're going to call it a row vector. A vector is going to be just a single row or just a single column. Part D, 1, 2, 3, 4 rows and 1 column, which makes this a 4 by 1. The size is 4 by 1, or the dimension is 4 by 1. This is a vector, but specifically it is a column vector. Now, if you go back to problem 1a, it's not a square and it's not a vector. It's neither. We would just call it a matrix. It doesn't have a special kind of name. Number 2, find the given element of the matrices from example 1. Now, I did make a typo here. A23 wouldn't make any sense. You'll see why here in a second. I want you to change that to A32. Now, it's a subscript 32, so it's a big A and a little bitty subscript 32, but we read it as A32. So again, you go back to rows before co's. We're talking about rows and columns. So the 32 is really talking about the third row and the second column. So we want to go to matrix A into the third row and second column. A32 is equal to -1 because it's the element or the number that's in the third row and the second column. So when they say B31, all you have to do is find matrix B, row 3, column 1, that's this element right here, -4. B31 is -4. C14, matrix C, first row, fourth column, -2. D31, go to matrix D, row 3, column 1, is this 0 right here. Simple enough. Matrix equality. 2 matrices are equal if they're the same size, meaning same dimension, and, corresponding elements are equal. So you look at this first example here. These matrices are equal only if, and so you look at it, they're supposed to be the same size, but they have the same size. They're both 3 by 2. And so that's good, but they also have to have corresponding elements that are equal. And so the only way that this could possibly work is if that y value equals 33. That would make their corresponding elements equal. Then those 2 matrices are equal. The next example, these matrices can't be equal. Well, they can't be equal because they're not the same size. One of them's a 2 by 1, the other's a 3 by 1. Because they aren't the same size. Have to be the same size, have to have corresponding elements equal. Adding and subtracting matrices. So this is kind of the main event. You can add and subtract two matrices only if they, and let's say it this way, are the same size. When you look at example 3, find the sum if possible. If possible suggests that sometimes it's not going to be possible. So again, they have to be the same size. Well, you look, you've got a 2 by 3 and a 2 by 3. Both of these are 2 by 3s. So yeah, it's going to be possible. And how you do that is you just add the corresponding elements. So this is the first row, first column. You add that with the first row, first column of the second one. 3 plus 1 is 4, and that goes in the first row, first column. So we do that all the way across. First row, second column, 4 plus negative 2 is 2. First row, third column, 5 plus 4 is 9. Keep going. 1 plus negative 2 is negative 1. 2 plus negative 4 is negative 2. 3 plus 8 is 11. And that's the sum. Problem number 4, perform each indicated operation if possible. We'll look at the 4 examples. One of them is not possible. Try to figure out which one. If you said part D was not possible, you are correct. It's not possible to subtract those two matrices because they're not the same size. The other 3 are possible because they're all talking about the same size matrix. Well, the first one's easy. 4A, all you're doing is adding 0. 2 plus 0, 1 plus 0, 3 plus 0, 5 plus 0. That's simple. You're adding a 0 matrix. You're going to get back to the original matrix, of course. Part B, again, add your corresponding elements. First row, first column. 2 plus 10 is 12. 1 plus negative 4 is negative 3. 3 plus 7 is 10. 5 plus 25 is 30. Make sure you put the brackets around. The brackets are what indicate that you're talking about a matrix. 12, negative 3, 10, 30. Part C is actually the hardest one. It's just harder to do subtraction. Trust me on this. Okay? It's hard to subtract negatives sometimes. And I know you can do it in your head. I know you're able to, but it does get confusing. And so that's why I would recommend this. When you subtract, we've always been able to subtract by adding the opposite. Ever since we started talking about negatives, subtracting is adding the opposite. So what I would recommend is you say plus the opposite of all of these. So I'm going to add the opposite, or same change opposite if you've learned that, but I'm going to change it into an addition problem because we're just better at addition problems. So then just add your corresponding terms. 3 plus negative 1 is 2. 4 plus 2 is 6. 5 plus negative 4 is 1. 1 plus 2 is 3. 2 plus 4 is 6. 3 plus negative 8 is negative 5.